Hello guys, welcome back to a video of the question guy, and today we're going to be doing a question which it's basically physics, but it involves a lot of buoyancy and a lot of analyzation to solve it. So yeah, let's just get started. So a block of wood is placed in water at rest, so the block of wood is static or not moving. And the volume exposed to the surface of the water is 54 centimeter cubed, as shown in figure 1. Now, a metal block with a volume of 20 centimeters is placed on the top of the block, and the wooden block is fully and exactly submerged in water, as shown in figure 2. Find the density of the metal block. Now, in number 2, in diagram 2, figure 2, the metal block is not submerged nor partially submerged, but on the surface of the water, meaning it's like just touching the water level. So let's start. Ignore case 2 and let's focus on case 1. So the buoyant force of case 1 is just equal to the gravity of the water, the weight of the water, the force on the water. So why this is just because that it's not submerged, so that it's floating. That's why its balance is static. So that means that because this up force is equal to this down force, that's why it's floating. So what we have is yeah, we'll leave it at that. We don't need to now. Don't expand it yet because we need to consider the second situation. Buoyant force 2 is equal to the gravity of the wood plus the gravity of the metal. Because now we added the metal's weight. And it's still floating, right? These two forces together still don't make it enough so that the up force doesn't make it sink. So let's think about this. If we want to, since we want the density of the metal block, let's try to isolate this. How do we do that? Well, if we look at this, if we subtract this this bottom one, buoyant force 2 is equal to gravitational force of the wood plus gravitational force of the metal minus buoyant force 1 is equal to gravitational force of the wood. We'll just isolate gravitational force of the metal. What that looks like is this. This is 1, this is 2, 2 minus 1. Buoyant force 2 minus buoyant force 1 is equal to gravity of the metal. Now expand this out, you get density of the water, volume displaced 2 minus density of the water, volume displaced 1 is equal to mass of the metal, because we're in this, there's always gravitational acceleration, but we can get rid of it. Put these all together, find the common term, rho of water density. We have this, so rho water times the volume displaced 2 minus volume displaced 1 is equal to mass of the metal. Now, pay attention here. So, the volume exposed to the surface of the water is 54 centimeter squared. This section here, shaded at the top of the first diagram, is 54. If this is fully submerged, which is the volume, so this volume displaced 2 is the whole square, right? It's this whole square. Volume displaced 1 is this section inside the water. Now, if we were to subtract the whole thing from the section in the water, wouldn't we get 54? Like, let's move this over here. Think about it. We have the whole thing inside the water, then this section in the water. This section plus the top 54 is equal to the whole section. So the whole section minus the section in the water is equal to the top section, which is 54 centimeters. So we have rho of the water times 54 is equal to the mass of the metal. Now, We can expand this. Rho water times 54 is equal to rho metal, volume metal. And then we can do stuff like plugging in most of the numbers. So we have 1 times 54 is equal to 20 times rho metal times 20. I don't know why I cared, but I cared. Then we can divide by 20, so that's 54 over 20 is equal to the density of the metal. So the density of the metal is equal to 2.7 grams per centimeter cubed. And that's the answer. I don't know why I circled everything. That's the answer. Thank you for listening to another video of The Question Guy, and I hope you learned something today.